The key idea in a permutation is that the order matters, but in some cases, if we're trying to form a number of arrangements, which is just another term for putting things in in a position where order matters, sometimes certain objects within that permutation might be identical. Like if you're thinking about electing students, every student is an individual. They're all different. So we would not say that there is any overlapping outcomes where there is kind of duplication amongst the objects within the set. But another very common type of permutation question would be, how many different ways can you arrange these letters? Like say, for example, number 19 says, find the number of arrangements of the word banana. And we can see that there's a lot of the letters A and N. If you're a Scrabble player, this is something you're familiar with. There's a lot of different ways you could arrange that. And if you're a gamer, thinking about the different arrangements and how many there could help you figure out other words or better words that you could form with a group of letters. But I've just chosen a random word here that has a lot of repeated letters. But basically, let's go ahead and look at this formula for how a permutation works when it has like objects, meaning that things are exactly identical, like banana having a lot of letters in common. We could permute these, and technically there would be 7 factorial unique ways of writing a word with 7 letters. However, when there are duplicates, there would be less unique words because, if you swap the order of A and A, that would still be banana, and technically it would be different permutation because permutations treat every single object as different. So it's as if there are n objects of which R1 are alike, R2 are alike, and so on through Rk, then the number of different arrangements of all n objects where alike objects are indistinguishable is equal to n factorial divided by the product of the individual factorials. Or in other words, you want to take the raw permutation of those objects and divide it by the permutations that would be duplicated by having repetitions. So let's just apply this formula here. So here, n is going to be 7 because banana has 7 letters in it. And then R1, essentially it's like we want to look for all our duplication. Letter A there were 3 letter A's. So that would be R1 would be 3 and R2 would be n, which was duplicated twice. And technically you could say, well, B is sorry, there's only 6 letters in banana. What am I thinking? Anyways, and then B is our other choice. Technically, you could say, well, R3 is equal to 1, but if you plug in 1 factorial, that's 1, and that's actually not going to matter. So you only need to worry about using the duplicated entries in the formula. So basically, what I would be left with is 6 factorial in the numerator, which is just the raw permutations of 6 objects, and divide that by 3 factorial times 2 factorial. And essentially, 3 factorial would be 6, 3 times 2. And all that's kind of doing is saying, well, of all those A's, there would be 6 unique ways of scrambling those. So within this raw 6 factorial number of permutations of those 6 letters, basically, there's going to be duplicated, all those A's are duplicated 6 times. So we're going to throw out basically 5 out of 6 of those by dividing by 6. And same thing with the 2 factorial, since there are 2 duplicated n's, the duplication of them would be treated as unique permutations, so we want to divide away by that. That's sort of how I remember this idea and why this formula makes sense. But basically, we would have 6 factorial, which is equal to 6 times 5 times 4 times 3 times 2 times 1, which we don't need. And that's all divided by 3 times 2 times 2. So we might even be able to do this without a calculator, but that would leave us with 6 times 5 is 30 times 4 is 120 divided by 2 is 60. So what we should have is 60 unique arrangements of the word banana, such as nabana, or you could come up with them all if you were patient enough. But obviously having formulas like these makes it a little bit easier to solve probability problems. And in a couple videos after we talk about combinations, we'll look at one of the examples from the book and see how we can kind of put all this to use in solving more difficult probability problems.